How do we decide which resonance structure of a given molecule is the best or is the most stable? Here are a set of 5 steps, checkpoints that we would use to determine if a resonance structure is preferred over the rest. Number 1, a more stable resonance structure will have maximum number of covalent bonds with complete octet. So you want to consider first and foremost octet rule. If there is anyone that has full octets, meaning 8 electrons around elements, except of course hydrogen, which takes 2, and the other ones don't have it, that's what you want to go for. Number 2, a more stable resonance structure will minimize the number of formal charges. So you have to minimize the number of formal charges. If possible, don't have them. But if you have them, go with the one that has the least formal charges. A more stable resonance structure will have the least separation of charge. This means you don't want the charges to be far apart. You want them to be as close as possible, meaning the negative and positive. Of course, you don't want the negative and positive close together. That will cause like charge repulsion. You want negative and positive charge to be quite close. For example, if you have this structure, those two are quite close. Probably that came from a resonance structure of a carbonyl. If you push electrons towards the oxygen, this is the resonance structure you get. So they are quite close. When they are quite close, it's good because you can easily make a double bond to neutralize the plus charge below, and of course the negative charge will disappear. Number 5, number 4, I think, a more stable resonance structure will have a negative charge on more electronegative element. So again, you want to have a negative charge on oxygen and not on carbon in this case. You don't want this situation where you have a bond with a more electronegative element having positive charge, because if an element is electronegative, it really wants electrons. You don't want to put a plus charge there, which implies it doesn't even have electrons that it should have. So you want to have a negative charge on the more electronegative element. Remember the periodic table, the likelihood of attracting an electron, the electron affinity, otherwise called electronegativity, increases left to right and bottom to top, fluorine being the most electronegative. So for carbon period, you have CNOF. Oxygen is more electronegative than carbon in that row. I believe it's the second row of the periodic table. Number 5, a more stable resonance structure will have a positive charge on the least electronegative element, which is again illustrated above. You want the positive charge on carbon and not on oxygen, because carbon is less electronegative, which means it's more electropositive. So let's look at an example of the cyanate anion. This is one of the resonance structures, but if you want to generate and form the other one, you'd move this in to make a double bond, which is this. You have a lone pair next to a pi bond. So you start from the lone pair, make a double bond, and then to conserve 4 bonds on the nitrogen, since you're creating one, we have to open this up towards the carbon. You'll end up with this structure. Formal charge will change from negative to -2 on that carbon if you do the formal charge calculations. Formal charge equals to valency of the element in the periodic table. Carbon is in main group 4. I have 4 non-bonding electrons, and then I have 2 bonds on it. That gives me -2. Nitrogen will stay the same. The valency of nitrogen is 5. There's no lone pair on it, and there's 4 bonds around it, so it's +1. Then oxygen will stay 0. Now if you add -2 and +1, you get overall -1. So it's still, the overall charge stays the same, I see. Okay, and then let's try and make the other resonance structure. We are borrowing 1 more lone pair to make a triple bond right there. And then we are making a pi bond, which now becomes triple. And then to conserve 4 bonds, octet rule on the nitrogen, we have to push over the lone pair. So the lone pair is right there, is pushed over. You had a double bond, now it's a single bond. You do your 4 more charges on this carbon. Valency of 4. There's 6 non-bonding electrons, and there's 1 bond. That will give you an answer of -3. That's the formal charge of carbon. But -3, positive, and positive on oxygen. If you do for oxygen, it will be positive. The overall charge -3 plus and plus, you get -1. Again, the overall charge is -1. Seems like the overall charge is conserved, but now who is the best out of all this? Who is the best? I'm looking along and I'm seeing that all elements, they seem to be octet with 8 electrons around them. So rule number 1 applies. If we want to minimize the number of formal charges, then we would want to, let's see, we are going over on negative. I don't think that's a strong point. Let's keep going. A more stable will have less separation of charge. The charges are quite close, that's fine. But I see here it's not evened out. You see how it's evened out, negative, positive, negative. Here is -3 plus plus, also not evened out, already pointing out structure 2 and 3 is not good. I'm leaning towards A. A more stable structure will have a negative charge on the more electronegative element. The more electronegative element here is oxygen. Okay, so we have oxygen having a negative. Here oxygen does not have it. Here oxygen has a positive. Obviously you don't want that. Don't want the electronegative elements having a positive. Okay. Here it does not have it, which is a good thing when it doesn't have it. But the problem is that the least electronegative element here has more negative charge. We said that we want the negative charge on the more electronegative. So this is out for this structure. The best structure will be A. A is the most possible way the cyanate ion will exist. That will be the resonance structure. And that's how naturally, most likely, cyanate anion will exist based on these rules. Let us use the same rules to judge the resonances of methane diazonium cation. This is one of the resonance structures. If we want to get the other one, probably push towards the plus charge. One of the rules of drawing resonance structures is to push electrons towards the plus charge. If you do so, this nitrogen right here will have a lone pair, and if you do the formal charge of that nitrogen, new nitrogen will be, nitrogen is main group 5, valency of 5, 2 non-bonding electrons, and then you subtract the 3 bonds, the answer becomes 0. So there's no more charge here. It was positive, here it's 0. However, for this other one, this other nitrogen, valency of 5, 2 non-bonding electrons, minus 2 bonds, I get a positive 1. Okay, so here the nitrogen here is having a positive, and it lost its octet. You see you have 1, 2, 3, 4, 5, 6 is a sextate. That's a problem based on the octet rule. This one has all octates. This is the most stable one, just based on rule number 1. Okay, let us now consider the phenoxide anion. It tends to have 4 unique resonance contributing structures. The last one is just a repetition of the first one. They are quite similar. Which one is the most stable? If I look closely, all the elements should be octets. Remember that on the ring you have implied hydrogens. You can draw them and you will see that all elements around the rings are octets. So this one passes. A more stable structure will minimize number of HOMO charges. All of them have negative charges. That passes. A more stable resonance structures will have the least separation of HOMO charge. I only have one charge, so I can't consider charge separation, meaning I can't consider how far the negative is from the positive. So that does not apply. A more stable resonance structure will have a negative charge on the more electronegative element. Remember that electronegativity increases left to right of the periodic table towards fluorine and bottom to up. So in this case, all I have is carbon, hydrogen, and oxygen, and I see that I have a negative charge on oxygen. Here it's on carbon, here it's on carbon, here it's on carbon, that's on oxygen, but it's a repetition of the first one. So I believe just based on this point, I can use that point to judge who wins. The first molecule is going to be most stable because I do have a negative charge on the more electronegative oxygen, which means the oxygen wants to hold the electrons to it, high affinity of electrons. So molecule 1, resonance contributor 1, is the most stable. You want the negative charge on oxygen rather than on carbon for stabilization. I hope that helped.